streaming. And what we talked about on Tuesday, was this topic here, physical states and so on and so forth. And I think your question has to do with the circuit that we talked about. This one. Okay, so what do you want me to talk about it about? I mean, what?
For n transistor, we need to know the value is one. The control sign is turned on. So should be go through, right?
Yes. So when an N transistor, when the gate of an N transistor is a positive voltage or one, then the transistor is quote unquote on, which means it connects.
Yeah.
It connects from the source to the drain,
So
and it allows negative charge to go in this direction.
sub to drain, so it should from the flow from the low to high, right?
Well, as far as we are concerned, we just have to know that it connects.
Okay.
Yep, it completes the path.
But I see your lecture said the N transistor should flow from the low voltage to high voltage. What does it mean?
Well, because for an N transistor, the flow of charge is with respect to negative charge. With a P transistor, it is with respect to positive charge. This is the source of positive charge. This is the source of negative charge. So you can look at current in either direction. Okay, so you can say, oh, we have negative charge going from here to here, or you can say we have positive charge going from here to here. Okay, so positive charge is just positive charge. Okay, and this is the source, and negative charge, for negative charge, this is the source. But as far as we are concerned, we just have to know whether the transistor is connecting or not connecting. So we just need to know about the logical consequence of turning on and off the transistors, but not so much the physics behind the whole thing. Mm-hmm. Any other questions related to the NAND 2 gate or the NAND 2 gate implemented by transistors? No questions? All right. Cool. So just to remind you what we talked about on Tuesday. So we analyzed the circuit. Okay, all of these are analysis on the circuit, and then what we did was we talked about the implementation of a negation, logical negation gate using a NAND. So we translate into a NAND gate here. We talked about the usual AND gate, which is conjunction, and it takes 3 NAND gates to do it, but nonetheless we can do it. Okay, so the bottom line is we can do it. And then we also talk about the OR gate, and we can implement a OR gate using also 3 NAND gates. So it may not be the most efficient way to implement OR, but it is doable. So the bottom line is, every single logical operator that you have learned in cisp310, we can use transistors to implement those. Is that okay? So it's big in 2 ways, because one, it means that things can be done physically. It's not really just in your source code. Okay, and number 2, it is also important because now we have to kind of equate true as a higher voltage and 0 as 0 volt. So we are equating, or we are assigning meanings to physical quantities. Is that okay? All right. So what we'll do today is to continue to talk about representation of things, but this time we'll talk about numbers and values. So this part gives you a little introduction to what is the difference between a number as opposed to a value. Okay. So if I ask you how many fingers I've held up here, that's a quantity. It is a value. Okay. The moment I say 4, F-O-U-R, it is the representation. That's a number. Okay. So a number is only necessary when you need to communicate a quantity to another person. But when you're thinking in your head, what word you choose to use or what representation you choose to use to represent this quantity is entirely up to you. Is that okay? So if you are, if you're like me, English as a second language, you might actually think of this as a native language, okay? That is not just four. You might think of it in Spanish, Russian, Vietnamese, Chinese, and so on and so forth. But that's really just a label of the quantity. So are we doing okay so far, making that distinction between a value, which is kind of abstract, as opposed to a number, which is a representation of that so that you can communicate with another person? So, okay, all right, cool. So with that in mind, we are moving on to base conversion. So this is the next slide. This is the slide that we're going to talk about today. And it has to do with, so it repeats a little bit of what I just talked about. A number is a representation of a value. And then it starts with base 10 numbers. So we'll kind of move really quickly past this until we get to here. And now you guys are required, okay, to read the actual text. Okay. Now if possible, do it before the class. If not possible, if you cannot do it before the class, you definitely need to do it after the class. Okay. In other words, everything in the notes can be asked in the exams. Okay, so I may not read every single word in my notes here, because that would bore me, not you, to death. Because to you this is all new, to me it is not. So it would bore me a lot. All right, but I would focus on certain things that are really important. So if you look at this as a base 10 number, okay, which is the usual way of looking at numbers, I can break it up, right? So this is 16.375. I can break it up into, it's 10 plus 6 plus 0.3 plus 0.07 plus 0.005. So does anyone want to challenge that or dispute that? No, that's pretty easy stuff, right? Then I can rewrite that. So instead of using 10, I say that it is 1 times 10 to the power of 1, right? Instead of 6, I say it is 6 times 10 to the power of 0, because anything raised to the power of 0 is 1. 0.3, we can do the same thing. It is 3 times 10 to the power of negative 1. 0.07 is 7 times 10 to the power of negative 2. And then the last one is 0.005, which can be now expressed as 5 times 10 to the power of negative 3. Is that okay so far? Okay. So but you can see a pattern here. Okay. So the pattern is everything in the last row is a quantity times a power of 10. This is the power of 10, power of 10, power of 10, and so on. And then it's not just some random powers of 10. It is a range of powers of 10, and then the powers are integers. Is that okay? But this is the bottom line of how we represent numbers, or how we use numbers to represent values. Every single digit of a number is representing a quantity of whatever base, maybe it's implicit, but whatever base raised to a particular power according to the place of that digit. Is that okay? So whatever is taking this place, which is immediately to the left of the point, is always specifying the quantity of the base raised to the power of 0. The one digit to the left of that, which is 1 in this example, is always representing the quantity of whatever base you choose to use raised to the power of 1. And then 2, 3, 4, 5, and so on to the left-hand side. To the right-hand side of the point, we are going for the negative powers. So immediately to the right-hand side of the point is the quantity. The digit is representing the quantity of whatever base raised to the power of negative 1. and then -2, -3, and so on as you move to the right-hand side. So is that okay? Do you guys all see a pattern of how a value is represented by digits in a number? Is that good? Okay. So obviously, what I have highlighted here on the projector is not very exciting. You guys know this already, right? So, but then we want to generalize the pattern. So that's why we have this part here. Let me highlight it and scroll it up a little bit. So this is nothing more than a formalization of how we represent values using a number. So in this case, D0 is the digit immediately to the left of the point. Okay, I just designate that digit as D0. And that specifies the number of 10 to the power of 0 when we're using base 10 numbers. And then D1 is the digit that is immediately to the left of D0. And that specifies the number of 10 to the power of 1. And then on the opposite side, D minus 1 is representing, which is the digit immediately to the right-hand side of the point. It represents the quantity of 10 to the power of -1. So we just keep going, on both sides indefinitely. So instead of using it, the first line, which is kind of like, well, what about D2? What about D -2? What about D3 and D -3? So instead of spelling out the individual terms, I'm using a sigma notation or summation notation. Is everybody familiar with the summation notation? If not, I can explain that. Okay? So everybody is comfortable? Because if you're not comfortable, yep. Yes, absolutely. So what I can do is I can show you the sigma notation and explain that using a C loop. Okay? So let's see if I can do that with a text editor here. Okay, there we go. So since I cannot really use a sigma, in plain text, I'm just going to use the word sum, and I equals to. Now I'm going to make it kind of abstract. So in this notation, you can look at sum as the sigma notation itself. I equals A is below the sigma, and then B is above the sigma. In other words, I am going for the series where I goes from A to B. So when I equals A is a term, when I equals A plus 1 is another term, and I keep doing that until I equals to B, which is the last term in the summation. Is that okay? All right. And what we're doing in the summation, I don't even bother to specify the expression. I just call that some kind of function applied to I. Okay, so f of I is basically a value that depends on I. Well, potentially depends on I, but it returns a particular value. So I'm just adding f of A plus f of A plus 1, f plus f of A plus 2, all the way up to f of B. So I'm going to expand the terms so that you can see, okay, this is just f of A plus f of A plus 1, oops, plus f of A plus 2, plus dot, 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 and we end with f of B. Is that okay? So if I were to write a subroutine or loop to do this in C, it's going to look like this. So for I equals to exactly A, I is less than or equal to B, because B, when I equals B, that's my last iteration I cannot get out when I equals B, plus plus I, and then inside the loop, okay, I need to do a little sum here, or whatever type, okay, whatever value type I choose to use, it doesn't really matter. So I'm using value as a type, and I have to initialize sum to 0, so we can do it here. Sum equals to 0, and then all I'm doing inside the loop for each iteration is to add f of I to sum. So when this is all done, when the loop is done, then the sum variable would have my answer. Basically, it becomes the value of the sigma notation. Is that Okay, all right. So do we have any questions about the sigma or the summation notation? Yep. Hmm? It can be implemented by a loop, yes. But mathematicians, simply says, okay, it's when you expand a sigma, it is each individual. There will be individual terms, and then those terms are dictated by the range of values that you specify, when you write down the sigma. Okay, is that okay? All right. So getting back to the notes, okay. So is this part okay? The sigma notation here. Because I'm just assuming that we're dealing with numbers that can have an infinite number of digits. Okay, so that's why I goes from negative infinity to positive infinity, because I don't know exactly how many digits we're dealing with. So I'm just saying, okay, let's assume it has an infinite number of digits. So I is the place of the digit that is of interest to me. So D0 is the one that is immediately to the left-hand side of the point. D minus 1 is the one that is immediately to the right-hand side of the point, and so on. But I single out one single digit and then multiply that to a power of 10 that is related to the place of the digit itself. So the further to the left, the higher the value of I, and then the higher power of 10 that I'm multiplying it with. Is that okay? Are there any questions relating this to what we talked about a little bit earlier? So to relate that, this 1 is going to be the value of D1. This 6 would be the value of D0. This 3 would be the value of D minus 1, D minus 2, and D minus 3. And then the places corresponding to all of these digits would be negative 3 for this one, negative 2 for this one, negative 1 for this one, 0 for this one, and 1 for that one. So are we good so far? Yes? All right. So I'm hoping so far, I have just introduced a representation that's kind of looking at the pattern of how numbers are used to represent a value. So V on the left-hand side of the equality is just a symbol representing the value that we are trying to represent using a base 10 number. Is that okay? So now the question is, what if we choose another base? What if we change this constant of 10 to B and just say that we are changing the base? Is that okay? I mean, is that doable? Is it possible? Absolutely. All right. So that's the whole idea of representing a value using some base, okay, using numbers of a particular base B. So I'm going to pause a little bit here to see if you guys have any questions about this part. No questions? All right. So section 5, which is right below this, is about converting a value V, or coming up with a representation in base whatever B we choose to use to represent a value V. Okay, so how do we do that? So what we'll do first is something that only some of you can do right now. Okay, because some of you may not have sufficient training to do this. Okay, so we are talking about using the least number of bills and coins as change to a customer at McDonald's. Do you think you can, you're qualified to do at least that part of a job, working at McDonald's? Okay, so let's go through some examples, and then I'll see whether you guys actually know how to do it or not. So let's say the change was $6.75. That doesn't look good. Let me try another one. $9. Okay, $9.75. That looks better. Okay. So how many of you would just go, I'm just going to give the customer 975 pennies? because that's the easiest way to do it, right? So here's a whole tube of pennies. It says 100, so I'll get 9 of those things, and then I'll count 75 more pennies and then give the entire thing to the customer as change. Well, technically you are correct, but your customers may not be very happy about that. Huh? Opposite way. Well, I have seen that at a Dollar Tree. Oh, okay. At a Dollar Tree, it's not just being paying by pennies, and there's a whole binder of coupons to apply to the items. So that took about half an hour just for that one single customer. Okay. So anyway, can we figure out how to use the least number of common bills and coins to come up with this amount? All right, so I'm just pretending that we don't know, okay? So let's just say that in the register at a McDonald's, the highest bill denomination is $20, okay? So you say, nope, 0 of those $20 bills. You move down to a $10 bill, 0 of those, and then $5 bills, right? 1 of those, okay? So once you take care of the $5 out of $9.75, you got $4.75 left. I'm going to ignore $2 bills because they are not usual. So we move down to $1 bills. So how many of those $1 bills do we need? 4 of those. So now we have taken care of the $9. We got 75 cents left. Let's not use half dollars, okay, because those are uncommon as well. So we move down to quarters. So we got 3 quarters, right? And then we don't have any dimes, and we do not have any pennies. So, huh? Oh, right, nickels. Nickels. Okay, was anyone particularly challenged by this activity? Nobody. Okay. Do you think I can pull someone from a remedial math class and still be able to solve this? Maybe, maybe not, okay? But most people know how to do this. And this is worse than base conversion. Much worse than base conversion. Because there's no regularity of the denominations. Okay, let's take a look here. So we're now taking a look at the multipliers to go from one denomination to the next. Okay, so we're going to start with the penny, and you need 5 pennies to make up a nickel. And then you need 2 nickels to make up a dime, and then you need 2.5 dimes to make up a quarter. And then you need 4 quarters to make up a dollar. So far I'm not seeing any repeating patterns, or even a repeating multiplier. And then you move up, this is a 5. Then you would think, oh, the next one must be a 2 and then a 2.5. Not exactly. Here's a 2, and then another 2, and then the next one up is a 2.5 for a $50 bill, and then back to 2 for a $100 bill. And that's my entire knowledge of denominations, because I'm not that rich of a person. I don't carry around like big bills. But there's no regularity at all, and you can do it. Why? Because you're used to it. So I'm going to say the same thing as I said yesterday to the other class. If you're immersed in something and you have been using it for years, even if that something is absolutely absurd, you'll get used to it and you'll think it's normal. Okay? So I'm going to introduce something that makes a lot more sense, but initially you will say, that is weird. All right? So now welcome to my kingdom and my fast food chain, where I do not use the normal denominations. So I'm going to use, I will start with a $32 bills, okay? So we have 32, and then 16, and then 8, okay. I hate this keyboard, it's not a very easy keyboard to type on. 1, And then the next one down is 0.5, 0.25, and I'll even have a 0.125. So these are the denominations that I use in my kingdom. Okay? I'll call it kingdom B for binary. But I want to come up with exactly the same amount, which is 9.75. Okay? So how are we going to do this? Okay, so we're going to go back and backfill those values. Okay? How many 32s do we need? 0. 16s, 0. We probably need 1 8, right? So after the 8, I only got $1.75 left, so I don't need a 4. I don't need a 2, but I do need a 1. That takes care of the $9. We got 75 cents left. So we'll take up one $half and $1/4, and we do not need any $8, right? But this looks kind of awkward, right? Because we are not used to it. But it makes a lot more sense. Because to go from one denomination to the next, it's always just multiplying by 2. 0.125 times 2 is 0.25, times 2 is 0.5, times 2 is 1, times 2 is 2, times 2 is 4, and so on. It's actually regular. There's a structure to it. It is self-consistent. So how come we are not using this? Well, you get that in base 10 too. 1 divided by 3, 1 divided by 7, 1 divided by 6, and so on. So there's no particular reason why we do not use this as opposed to the system that we already have. We're not computers. That's one thing, but we know enough now that the binary number system is actually a lot easier to learn and to work with. Okay, and yet we are not changing. I mean, we're not even metric. You go to a gas station, are you filling up in liters? No, you're using gallons. How many other countries still use gallons? None. Exactly. The United States is the only country still using imperial units, which is somewhat ironic. Cool. But the other thing I also want to point out is we have a binary number here. I just need to put a point here. Remember, the point is separating the number of ones as opposed to the number of whatever base raised to the power of -1. That is the separator. In other words, we have a binary number now. Okay, but you look, no, this doesn't look like a binary number. Try to rotate your head clockwise 90 degrees. Okay? I have pinched nerves, so I can't really do that, but I can do it mentally. But in this case, I'm just going to write out the number, just so that we can look at it. 001,001.110 in base 2. I use in parentheses a 2 to emphasize that this is a base 2 number as opposed to base 10 or some other base. It represents exactly the same quantity as 9.75 in base 10. It's just a different label. It's just a different name of the same quantity, the same value. Do we have any questions about this? Okay. Now, during this entire conversion process, did we use division at all? No. Did we use multiplication at all? Well, I suppose we can say 1 times 8 is a multiplication, but I know you guys are smart enough not to do that. Okay? So we only needed to rely on comparison and subtraction to do conversion to base 2. So that means it can be done really fast with a computer using a very minimal amount of circuitry. So that's kind of cool. All right, so that's base 2. Well, there are a lot of advantages to base 2, but I will kind of talk about that toward the end of the lecture. So right now we're going to focus on some other bases that makes absolutely no sense. Okay, unless you're some other kind of weird animals. So we'll talk about base 7. Okay, base 10 is familiar because we got 10 fingers, right? Base 7. Now, base 7 is really odd because it really is odd. Not only is it odd, it's prime as well. So it's a very awkward base to use. But can we use it as a base? The answer is yes, we can absolutely use it as a base. So we'll try to figure out, how to convert numbers to base 7 and how to convert numbers from base 7 back to the base that we are familiar with. Is that okay? All right. So I'm going to pick a number like 106, okay, in base 10. And I want to know, what is this number in base 7? So this is the question. So there are a few ways to do this. So I'm going to show you the long way of doing it first, and then we'll try to come up with some ways that are a little bit quicker. So when you convert it into base 7, I am going to designate these 4 digits as D3. So D3 is the most significant digit. D2 is the second most significant digit. D1 is the second least significant digit. And then D0 is the least significant digit. So I want to convert 106 in base 10 to a 4-digit base 7 number, like that. So D3 all the way down to D0, each one is an individual digit in base 7. So are we okay with that concept? Because unless we understand what we are about to do, it makes no sense to continue. Is that okay? All right. So now we look at the base 7 notation and go like, what exactly is D3 telling us? Well, D3 is telling us the quantity of 7 raised to the power of 3. D2 is telling us the number of, or the quantity of 7 raised to the power of 2. D1 is telling us the quantity of 7 raised to the power of 1. And then D0 is telling us the quantity of 7 raised to the power of 0. Oh, okay, so that's better. So once you figure out what is 7 to the power of 3, I think it's 353. So we are now saying this is actually just D3 times 353. This one is just 49. This one is just 7 by itself. And then the last one, I'm going to multiply by 1 even though it's trivial because the 1 is actually significant because 7 raised to the power of 0 is 1. Yes? It's 43, you're right. Okay, thank you. There we go. Oops. Insert mode. There we go. Okay, now it's better. Thank you. All right. That's better. Okay, so now we just look at the value that we are dealing with, which is 106, and go like, nah, we don't have any 343. Okay, that seems pretty obvious. Okay, so now we can say, oh, D3 has got to be a 0 because when you divide 106 by 343, the quotient is a 0. Is that making any sense? So everything becomes the remainder. So the remainder is 106 again. All right, so the next question is, of the remainder after we divide 106 by 343, if we divide 106 by 49, what do we get? 2. Okay, very good. So now we know D2 is 2 times 49. So that takes care of 98 as a quantity. 106 minus 98 is 8, right? I think so. Okay, so we have 8 left. So we now try to figure out how many 7s we have in 8. 8 divided by 7 has a quotient of 1. So that means D1 is going to be 1. Okay. So we have 1, 7. And then D0 is whatever is left, which is also a 1. Cool. So now we have our number. Because now we have figured out all the 4 digits already. 0 for D3, 2 for D1, D2, sorry, 1 for D1, and then another 1 for D0. So 0, 2, 1, 1 is representing the same value as 106 in base 10. That's the base conversion process to go from a value that we already know to a representation in a particular base. Is that okay? All right. And then someone's going to ask, why did you choose base 7? I mean, base 8, or base 16 or base 4 seems to make more sense in a computer science class. Well, choose base 7 because you're not familiar with it, even if you have exposure to binary numbers and stuff like that. And it makes sense to octopus, to octopi. Yes, I know octo means 8. But what if you want to hold on to your drink while counting? You gotta build that into the society, is entertainment and relaxing while doing something useful. So base 7 is perfect for octopi because they can use one tentacle to hold on to a crab that they're eating. So are we good so far? Yes? All right. Well, what about the other way around? What if I give you a base 7 number and I ask you, what is the value represented by this base 7 number? Can we do it in reverse? Well, let's check it out. So I'm going to give you a number in base 7. I'm going to give you like 4, 6, 1 in base 7. And I ask you, what is the quantity represented by 4, 6, 1 as a base 7 number? Now, I have to be careful not to call this 461 because when I say 100, it is specifying the quantity of 10 to the power of 2. So I cannot say this is 462. This is 462 as a base 7 number. All right? So we'll break it up. Okay, so what I do here does apply to every single base. Okay, so it becomes 400 base 7 plus 60 in base 7 plus 1 in base 7. Okay, so 400 in base 7 is 4 times 100 in base 7. Same trick in base 10 works here. This is just 6 times 10 in base 7. And this is just 1 times 1 in base 7. Cool. But doing this makes it possible for me to isolate the quantity from the power. Okay? So now I just have to deal with, but what is 100 in base 7? What do you think 100 is in base 7? It's 1 times 7 to the power of 2, right? So this becomes 4 times 7 to the power of 2. The number of zeros tells you to what power we are raising. So 100 means whatever base raised to the power of 2 because there are 2 zeros. Okay? What about the next one? It's 6 times 7 to the power of 1 because we got 1 0 in 1 0. And then the next one is just 1 times 7 to the power of, I don't see any zeros. Do you? So if there are no zeros, just give it a 0. Like that. Okay? Now, I haven't really talked about the other side, or digits to the right-hand side of the point. Those would just be going negative. Okay? 7 to the power of -1, -2, and so on. All right. So right now, we don't have any base 7 numbers left. Okay? All of these are base 10 numbers. Okay? Because you cannot write 7 as a single digit in base 7. Just like in base 10, we do not have a single digit to represent the quantity of 10. Okay? All right. So it is now just 4 times 49, because 7 squared is 49, plus 6 times 7 plus 1. And my arithmetic is pretty bad, but I know tricks to do this. So I think this is 156, right? Because it's nope, no, 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 nope. It's 196. There we go. Because I look at it as 4 times 50 minus 4 times 1, right? So it's 196. And next one is 42. And plus 1. Okay, this is the difficult part for me. Arithmetic is difficult. All I'm going to say is I will blame it on base 10. So the whole thing adds up to 239? Okay, all right. And that's a base 10 number. So is that okay? Are there any questions about either process, converting from a known quantity into a particular base, or going from a number in a particular base to the quantity that we are familiar with? Is that okay? All right. Cool. So I'm going to switch back to the notes a little bit here. So in the notes, when it talks about conversion to a particular base, it goes through a lot of discussion here, but in the end, it gives you the finalized equation. Now, this is really kind of useful in a way, but kind of not so useful in some other way. So let me tell you what the symbols are representing. B is representing the base. So normally we're dealing with base 10, but in the previous example, we're dealing with base 7. So B would be 7 in both places. I is the place of the digit that we are interested in. So once again, when I equals to 0, we are talking about the digit immediately to the left-hand side of the point. Is that okay? So D of I is the digit of place I. Okay? So we are only interested in one single digit in this conversion equation. V is the value that we are dealing with. Okay? Whatever quantity you want to represent in base B, that's V. Is that okay? So if I just give you this equation, are you just going to take it for granted? You can, but I would not. You should be skeptical, okay? If I just say, oh yeah, this is an equation, it's supposed to work. Well, at least, even if we do not prove that it works, okay? At least we can plug it in the previous example and check it out. Does that make sense? So we'll go ahead and check it out. So what we'll do is I am going to pop up the editor and put it on one side. And we got 2 examples here. So we'll just pick the second example. So we'll go ahead and say V is 239, which is the value that we are dealing with. Which place are we interested in? Let's say we're interested in place 1. And the base is base 7. So we should get 6 back, okay, when I plug in all that stuff. So now we'll go ahead and evaluate. So B1 equals to, that symbol is the floor symbol. So this thing here is called the floor symbol. The floor of x is the largest integer that is less than or equal to x. Is that okay? Let me say that one more time. The floor of x is the largest integer that is less than or equal to x. Yep. It is not, well, you can look at it as integer division in C, yes. So if you implement this equation in C, then you do not need to have the floor representation, because in C and C++, integer division is automatically rounded. Yep. Okay. So we are looking at the floor of 239 divided by 7 to the power of 1. So let me use extra parentheses here. And then when we get the result, we need to mod it. Okay, this is the C operator for modding. So we need to mod this with the base that we're dealing with, which is 7. Okay, so we'll work on this step by step. So this is the floor of 239 divided by 7. So I'm going to work out this math here. And the equation is 239. 239 divided by 7, it's going to be a recurring kind of thing. I'm just going to take a 34.14285. 34.14285. So it's 34.14285, blah, 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 okay? And mod it with 7. All right, so what is the floor of 34 point blah, 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 blah? What is the largest integer that is still less than or equal to 34.14285, blah, blah, blah? 34. Okay, so the floor of this is just 34. So we are looking at 34 mod 7. Oops. Which is the same thing as asking about the remainder of 34 divided by 7. And that turns out to be 6. Because the quotient is 4. 4 times 7 is 28. 34 minus 28 is 6. And guess what? That's exactly what it is supposed to be. Now, does this prove that the equation is correct? No. But it is a validation based on one single point and go like, yeah, seems to work. So are we good so far with that little equation that allows you to get a single digit when you're converting to some arbitrary base that you want to convert to? Is that okay? All right. So now we get back to the notes here. So base 2 is nothing more than simply saying the base that we are using is 2. Every trick that we have learned up to this point works. Okay? So why do we choose base 2 then? Okay, of all the bases that we can choose, why do we choose base 2? It relates back to something that I talked about at the very beginning of today's lecture. What did I talk about? On and off, right? The presence of a voltage versus the absence of a voltage, true, false, right? Well, we can reassign the things a little bit and we can say 0 volt means 0 and the presence of a positive voltage means 1. Instantly we got binary numbers. So that's why we like to have binary numbers. Cool. All right, so this slide is almost done. So we can get back, so I can give you a preview of certain things. So how a value is represented in the computer is basically just in binary. And here's a little conversion example, and so on. So now we want to get back to why is binary numbers a good system to use even for people? Because some people may think, it's really good for computers, but it's not so good for humans. Okay. Well, I would disagree with that assessment. Okay, so let me ask you. Okay, if you have a offspring, of that age, or if you remember, how you did it, let's think back in elementary school about 3rd grade. Okay, because that's when you start to learn multiplication and division. Okay, but you don't even have to go back that far. Let me ask you, what is 5 minus 7? Okay, let me write it on the in the virtual whiteboard here. Okay, 5 minus 7. What is that? Some of you will say -2, but in order to learn how to do multi-digit subtraction, you don't want to call this -2. You want to call this 8 with a borrow. Does that make sense to you? 8 with a borrow? Okay, I'll write it down and then I will say why that is the case. Okay, it's a borrow of 1. So to understand this part, okay, today is a good day for me to use my tablet because I don't want to do it on the whiteboard. So I'm going to do it on my tablet and turn it on first. So this might take a little bit of time to set up, but it'll be good once it's set up. How did you guys learn how to perform subtraction, multi-digit kind of subtraction? Don't tell me that they don't teach that anymore. Do they? Did you guys learn how to do multi-digit subtraction? Like, what is 100 minus 12? Okay, you have a systematic way of doing it, right? So that's multi-digit subtraction. And in order to do multi-digit subtraction, you have to understand the concept of borrowing. Okay, so you know that one little thing that you write, on the next column, you may not remember it's called a borrow, but it is borrow. Okay, so let me check on my tablet. Okay, is it up? Yep. And then I need to fire up my visor. It's a screencasting app, so I can cast the screen of my Android device onto the PC, so it's now recorded as a part of the stream. All right. So there's a bunch of upgrades. Fine, fine, and fine. And okay, it's getting there. It just takes a little bit longer than usual because I haven't done it for a long time. So the one that I need is called lecture notes, and this is for school 440. And let's add a new notebook. Create and open. Okay, doesn't look like it's gonna connect soon, so I'm gonna close it and reopen. There we go. Ah. Oh, crud. Doesn't work. Well, I can do this portion on the whiteboard because, it's something that you should be familiar with anyway. I'm just reminding you, how to do it. So let's say we are dealing with 102 minus, 68. Okay. So this is multi-digit subtraction. So now we have 2 minus 8, right? But you don't want to write down negative 6 here. Doesn't make sense. Instead, what you want to write down here is a 4 with a borrow. Does that make sense? Is it 4 with a borrow? Yep, it is. So the idea of a borrow, okay, if you just kind of focus on this part, okay, so don't even go any further. It's the same thing as asking, okay? I got $2 in my pocket, okay? There's a bully outside the door who's going to ask me for $8, or otherwise I'll get beaten up, okay? I got only $2, but I got to pay the bully $8. I don't want to be beaten up, so I'm going to have to borrow. Now, the trick is when I borrow from the next digit, I'm going to borrow a 10. I'm not going to borrow a 1, I'm going to borrow a 1 times 10. Because the amount I'm borrowing is always 10 times what I'm responsible for. Is that okay? So once I borrow the 10, I add it to the 2 that I already have, which is 12, right? I walk outside with my $12. The bully says, give me 8. All right, here's your 8, and I got $4 left in my pocket, right? But I have to remember that I actually owe someone $10, and that's what this borrow of 1 is indicating. Is that okay? So now I can just complete this subtraction. 0 minus 6 is a 4 with a borrow, and then 4 minus 1 is a 3, 1 minus 1 is a 0. So 34 is the difference between 102 and 68. Is that okay? So is this reminding you what the concept of borrowing is? Yes? Okay. So now what we do is we look at a table. 0 to 9, those are all the available digits in base 10. 0 to 9, those are all the available digits in base 10. We'll call this x and we'll call this y. And then for each cell, I just have to figure out what is x minus y. Okay? But there are two things I have to know about x minus y is, do we have a borrow? And what is the answer? So to give you an example, 3 minus 6 has a borrow of 1, but the actual amount left is the same thing as 13 minus 6, because I borrowed the 10 already, and 13 minus 6 is 7. Okay? So this is a pretty big table. 0, because we got 10 rows and 10 columns, which makes out to 100 entries. Somebody's going to say, but subtraction with 0, minus 0 is trivial. Fine. Remove one row. You still have 90 items. And then there are some easy ones that you can easily go like, oh, that's trivial as well. But in the end, you still have a lot of entries in this table. And that's why subtraction takes longer to learn compared to addition, because addition is at least commutative, right? A plus B is B plus A. So that means you can fold the table along the diagonal line and go like, I only have to remember 1/2 or the triangle of the entire square. But subtraction is not commutative, so you got to remember the entire table. Is that working okay so far? All right. What about binary number subtraction? Okay, so with binary number subtraction, we have 0, 1, and 0, 1. That's the entire size of the table for subtraction in binary. Doesn't look too big to me. 4 items. Of the 4 items, okay, some are trivial. So we'll use the same indication here. When you look at the columns, relate to values of x. The rows relate to the values of y. Okay, so this one is asking, what is 0 minus 0? What do you think the borrow is for 0 minus 0? There's no borrow. Okay, so we say borrow is 0. And then what about the result of the subtraction? Also 0. This one is corresponding to 1 minus 0. Okay, what is the borrow of 1 minus 0? Do you need to borrow? No. Okay, there's no borrow, and the result is 1, right? What about this one? This one corresponds to 1 minus 1. Do you need to borrow? No. So borrow is a 0. The result is 0. Very good. So the only one that looks kind of tricky is this guy here. This is 0 minus 1. I got nothing in my pocket, but the bully wants $1. What do I need to do? Borrow. But whenever I borrow, because this is in base 2, this is a 1 here. Because this is in base 2, whenever I borrow, I'm borrowing 2. Okay? So I borrow 2, I give 1 to the bully. I got how many left? 1 left. So the result is 1. That's the entire subtraction table in base 2. I can explain this probably to elementary school students in half an hour, and we are done with subtraction. As opposed to days and days and days and days of practicing so that you can remember, so that the kids can remember this entire table of 90 items at least. Is that making any sense? No, it doesn't make any sense at all. Because if binary is so easy to deal with, why are we not using it? Yes, so numbers can get pretty long, okay? So in order to express, 4 billion something, you will need 32 binary digits. But we have ways to get around that one too, because the conversion from base 2 to base 16 is a snap. It's just looking up things, okay? And in base 16, a 4 billion quantity only requires 8 digits, okay? So yes, I understand binary by itself, has a problem of, you're dealing with really, really long numbers because you need more digits. But we can easily convert from binary, which is base 2, to hexadecimal, which is base 16, using a table lookup method. It doesn't take much time at all. Okay? So the bottom line is, just repeating what I said a little bit earlier, things that are absurd looks normal when you're immersed in it for many, many years, and people and everybody around you do the same thing. So absurdness looks normal in those situations. Base 2 makes a lot more sense. It is a lot more logical to use. It's easier to learn, and yet we don't do it because everybody else is doing base 10. And we only do base 10 because we got 10 fingers. Yep. No, that's a 1.
Yeah, it's 1.
That's a 1.
Oh.
Yep. It's a borrow of 1.
So it's 0 minus 1, right?
Hmm?
It's 0 minus 1.
Yes, this is called. Yeah, we'll get back to this table later, okay? But all I'm doing is to illustrate why base 2 actually works, not only with computers, but even with humans. It makes more sense. Are there any questions about base 2? Well, since we are on this topic, we might as well, do the whole thing, okay? What about addition? 0 plus 0 is 0 with no carry, right? 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. The only tricky case in base 2 is when you have 1 plus 1. 1 plus 1 is kind of the same thing as 5 plus 5 in base 10. It results in a quantity that you cannot use a single digit to represent anymore. So you go like, oh, that's a 0 with a carry. And that's the entire addition table. You don't have those really awkward things like, what is 9 plus 5? 9 plus 5 is 4 with a carry in base 10. And how many cases do you have to memorize in base 10? Well, you have the 100 item table, half of which is identical to the other half because of symmetry. So you end up with 50 items. Of the 50 items, the entire top row is useless because you have 0 plus something. So now you minus 10 of those items. You get 40 items. So we are still talking about a pretty good number of things to memorize for base 10 addition. This is the entire table for base 2 addition. Done. So then you move on to multiplication. Okay, the multiplication table in base 10 is about the same size as addition because it's also commutative, right? So how do you know that 5 times 7 is 35? You know it because you have memorized it, right? What about in base 2? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Done. Multiplication in, what, 30 seconds? So the mechanism of binary numbers is actually far, far, far more easier to learn compared to base 10 numbers. Okay, we're not used to it. We look at binary numbers as if this is so alien. It's so weird. Only because we have been submerged in base 10 numbers for so long that we don't think about these things, anymore. So are there any questions about all of this stuff? We'll get back to base 2 subtraction and addition in a different slide. So don't worry if you don't get it today. It's fine. It's not a problem. All I want to do is to illustrate why base 2 is actually a very easy base to work with.
Just to clarify, that last multiplication you were doing,
Uh-huh.
you weren't doing that to represent 35, were you?
35?
You asked like 7 times 5 is 35, and you memorized that, but then you weren't doing that multiplication right there to represent 35, right? The 0 times 0, the 0 times 1.
Oh, this is a base 2 multiplication table.
Right.
Right.
But you weren't doing that to represent 35.
That is correct. You're correct. I was not using it to represent 35. Yep.
So when you borrow, you always borrow the base amount, right?
Yep.
Whatever the base is.
Yep. So in base 10, whenever you borrow, you're borrowing 10. In base 2, whenever you borrow, you're borrowing 2, and so on. Yep. So are we good so far with the topics today? Base conversion. We pay some really kind of odd attention to base 7, because if I just focus on base 2 from day 1, from the beginning of the class, you guys would just be specializing in base 2, and that's the only base you know how to convert to, and the only base that you understand. But I want you guys to understand number representation in general, so that's why I picked a base that is really awkward to use, which is a 7. But it also goes back to the point that you were able to, okay, let me go back to the editor here, but you were all able to come up with the change at the very beginning of this class. In other words, you already know about the concept of conversion into a different base. This is even more awkward, because look at all those multipliers. They're all over the place. But you can do it. Okay? But regular base conversion is just, easier. It's just that we never think of it that way, and that's why it feels kind of awkward and feels kind of difficult. But in reality, once you get used to it, it's easier than the currency problem at the beginning of the class. So it's a perspective kind of thing, how you look at it. All right. Any questions before we take a break before the lab? No questions? Yep.
Tempted to ask about division.
Division in base 2? It's actually pretty easy. Okay, well, since we got 5 minutes, might as well give you an example of how to do it, right? So we'll start with some random binary number as my dividend. And then we'll also use another number here in binary as my divisor. Okay, so I just randomly pick something. Okay, so what you do is you do the same thing that you normally do with division. Okay, so you ask, is there a 1 0 1 1 1 in 1 in base 2? It doesn't really matter what base you're dealing with, right? 1 0, is there a 1 0 1 1 1 in 1 0? Nope. 1 0 1? Nope. 1 0 1 1? No. 1 0 1 1 0? No. Is that making any sense? In other words, not even knowing what value it is representing, you know that 1 0 1 1 0 as a base 2 number cannot be as large as 1 0 1 1 1 as a base 2 number. Is that correct? Cool. All right, so we move on to this one. You go like, we got 1. How do we know this is a 1 and not a 2? Because it's a binary number. So you don't need to master multiplication first before you can do division, because you're only comparing. All you're doing is to expose more and more digits compared to the divisor until it is greater than or equal to. That is a whole lot easier compared to base 10 division, where you kind of have to guesstimate the quantity of your divisor in the dividend, right? Because this one is either 0 or 1. So you put a 1 here, and then you put 1 0 1 1 1 here. You do a subtraction. 1 minus. So this part I'm going to do really quick. We will get to this part, in terms of the detailed mechanism later. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. And then 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. Okay, so this is the remaining portion. I want to do a sanity check just to make sure that this is still less than or equal to that, because otherwise we have a problem. Okay, and then we put this one over here, and we say, yep, there's one over there, one of these in here, one divisor in here. So 1, 0, 1, 1, 1 goes here, and then we do another subtraction that looks really similar to that one. It is identical actually. So we got the same result, which is a 0, a 1, a 1, a 0, and a 1 here. And then we take this 0 down here. We say, oh, yeah, there's one of those. And then we put 1, 0, 1, 1, 1 here. That's a 1. That's a 0. That's a 1. That's a 0. That's a 1. And that's a 0. And then we take this 0 down here. We got one of those. 1, 0, 1, 1, 1. That's a 1. That's a 1. That's a 0. That's a 0. That's a 1. And then we get this 1 down here. We put 1 here. 1, 0, 1, 1, 1. Okay. And over here we got 0, 0, 0, 0, 1. And then we take this 1 down here. And then we copy that divisor down here. I'm running out of space. That's a 0, that's a 1, that's a 0, that's a 1, that's a 0. Uh-oh. I got, okay. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is 1 with a borrow. And then 1 minus 1 is a 0. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is 1 with a borrow. And then 1 minus 1 is a 0. So we only got 1, 0, 1, 0 left. And, but you can see the process is about the same. Okay, I'm not going to complete it because I just don't have room to do the entire thing. But the process is the same, with the exception that you don't need to master multiplication first. Because the only multiplication in binary that you need to do is between 0 times something and 1 times something. So all you need is just comparison and subtraction in base 2 division.
So once you're in there, all you have to worry about is the subtraction.
Yep.
That's
You have to compare first to see how many digits of the dividend you want to move down. And then but that's only a comparison issue. You just keep adding more digits and then compare until the dividend portion is greater than or equal to the divisor portion. Then you subtract the divisor from that portion and put a 1 in the quotient and then move on the same way. All right. So I'll see all of you at the lab. If you have a laptop computer, that would be very helpful, because we only got 31 computers in the lab.